Heyo! It's Football Fairy Friday! Is everyone excited? It has been, I'm sure you've noticed, quite the week. But hopefully we're going to push through and, try our best on this one, alright? Remember, no one can change who we are as people, and we were gonna try and help people before, and we're gonna try and help people now. Alright? We can do this. We aren't afraid of anyone. This Apex. Anyways, we are going to be doing a high school chemistry test. In fact, not just a high school chemistry test. In fact, I can show it to you now. Nope, not there we go. This is in fact August 2016. Yeah. No, this is 2016. Wait, but Chemistry 30 diploma examinations, August 2016. But if I look at the title of the document, it says release item 2017. Wait, I can fix this. Hold on. This will just take a second. Hold on, chat. It's not scuffed. Don't say it's scuffed. If you say it's scuffed, I'll kick you in the head. Chemistry 30 2018 released items. Nope, that's 2019. Please tell me 2018 isn't the only year they didn't release. Nope, they didn't release 2018. Okay, well, we can pretend this is the one I wrote. It's very similar. I looked at it and I thought it was the one I wrote, but it isn't. I've been fooled. I have been tricked by whoever released this. But yeah, I was just thinking, I'm gonna go through my answers, or I'm gonna look at this test, and I'm gonna try my best to explain it, and maybe I can instill a little bit of love for chemistry inside of all of you. And also, I mean, we just got some banter, you know? I've had quite the week, so there's a lot of stuff I want to talk about. Aside from that, I suppose we should, just get going. I'll just interject with my personal commentary whenever I so feel like. And we'll start with question 1. Shall we, chat? Question 1. Use the following question and answer. Question 1. 1. The reactants are glucose and oxygen. 2. The reactions absorb energy from the surroundings. 3. The reaction stores energy in chemical bonds. 4. The products are carbon dioxide and liquid water. Oh, one more thing I want to say before doing this test. So I'm pretty sure I liked chemistry a lot in high school, and I was an overachieving kid. I got a lot of high grades on my exams. Let's say I do have, a university diploma in chemistry, so I'm probably gonna do all right. If I get above 80%, I'm an apex predator, and you have to admit it. But otherwise, I'll admit, and I'm just like a dumb... Hello, Arca! Oh, you're running with the stream party of 5! I saw you were streaming, that's so hype! I was gonna check it out, but I was trying to fix my MapleBot, and it didn't work. Hello to all the streamers! I am the local needy bratty Fae, the apex predator, amongst everyone. Thank you for the headpats, Arca. If all the other raiders could please headpat too, that'd be perfect! !blue pad in chat. So that it's actually tracked by the little bot. But yeah, thanks for joining. We're writing a high school chemistry test. We're just starting now. Thank you for the pass, Gregory. I appreciate it. Thank you. We're just going through the first question here. I'll reread it, I suppose, since a bunch of people just joined. Okay, so use the following questions for answer 1. Oh, what is chemistry? Chemistry is... I like to think of it as the study of electrons. So, let's talk very, very fundamental for a second here. I wonder if there's blank pages included in this. Don't cheat. That was the answer key. Don't look at the answers and tell me all the answers, please, chat. Here, this is blank enough. So, fundamentally, there are smaller things, but just for the purposes of chemistry, the smallest things you have are your nucleus, the big part at the center of the atom, and you have the little electrons floating around it in orbitals. Boop. This is very important. When two chemicals react, like say carbon and carbon, they can bond in a few ways. In the case of carbon and carbon, they're capable of sharing electrons between them to form stabler bonds. And this is basically what all of organic chemistry is all about. The way these electrons can connect together to form larger molecules, basically. You can also have ionic bonds, which are similar, except you can imagine it rather than them. Someone just knocked on my door. Sorry, one moment. Sorry about that, chat. Literally, people came into my apartment right now and are walking around. There's no camera or anything, don't worry.
Okay.
Yeah, thank you.
You can have my audio, but not my video.
Yeah. So they're just looking around. Don't worry about it, I suppose. Continue where you left off. I like the molecular shape of you by Acapella Lessons. Is that a, that's gotta be, that's like an acapella band, right? Oh, it'd be sick, check it out. I'm sure it sounds great. I've never heard it before, though. A shout out again to the people who made the background music. So the other type of bonding, the other important one in chemistry, is that if this atom here really wants wants more electrons, we call that electronegativity. Electronegative, because it's, oh, excuse my poor writing. Whoop. Because electronegative, it's negative in electrons. It really wants more of them. So if it's strong enough, it can steal this electron straight off it, and you get an ionic bond, where this ends up with all the electrons, and this loses its. That's the foundations of chemistry, pretty much. These two types of bondings are what pretty much all atoms do, and these kind of reactions are what chemists study. How is everyone, by the way? I've had quite the freaking week. A lot has happened to me this week. I've gone way more exercise this week than I have previously. I've had to, I have all these boxes for shipping for moving out, and I've had to carry them around just to get them to the post office. And they are not light. That is not a fun walk. Could be way worse, though, to be honest. It's only a 15-minute walk, but man, I wish I still had my car. I miss Scoopy. Scoopy was a great car. Are the people coming new tenants touring the place? Yes. I think they already left, maybe? I'm not sure. I hope I didn't scare them. I genuinely had no idea they were coming. But it's okay, I guess. I'm sure, you know what, they'll have to live with it. They're the ones coming into my place. So the reactants are glucose and oxygen. The reaction absorbs energies from the surroundings. The reaction stores energy in chemical bonds, and the products are carbon dioxide and liquid water. The statement above that apply for photosynthesis are numbered what? Photosynthesis, as you may be aware, and please feel free to ask questions if you ever have any, is a process by which plants take in carbon from the air and sunlight to create to create sugar. And this process is basically storing, you know how I said that you can form covalent bonds between two carbon atoms? This is what photosynthesis is doing. It's forming these bonds so that this little bond can act as a battery in the sugar, and they can release it later to get more energy. Whoa, whoa. Energy out. And that's what powers the plants. And then when you eat the plants, those sugars go into you, and you process their sugars. And that's what powers all life on Earth. Woo! So, which of these statements are true about photosynthesis? That means that it's not one because it's producing glucose. So many bonds forming, kinky. I know, right? people have described carbon as the slut of the chemistry world because it's so willing to pair up with other compounds. In fact, these bonds are so common that they're what make up you and all life on Earth. That's why we're carbon life forms. Sorry, I'm a little out of breath. I don't know. I'm just a little nervous, I think. It's been a long week and I just need to de-stress a little, you know? But yeah. So 1 is not true of photosynthesis. Reaction absorbs energy from the surroundings. Well, it does. It absorbs the sunlight that's coming in, right? So true, 2 is true. The reaction stores energy in chemical bonds. Again, that is true. That's exactly what it's doing. It's taking that sunlight power and putting it in chemical bonds for later use. The products are carbon dioxide and water. That is not true. It is taking in carbon dioxide. And also, it's important to keep in mind, H2O is required for the reaction as well, even though I didn't write it out fully. So, if that's the case, that means that, oh, I got a follower. Oh, a new Faye friend. Thank you, Julie Q. I really appreciate it. Thank you for becoming a Faye friend. I hope you have a good time. And I hope you have a good day, too. Oh, thank you, Gregory5. I really appreciate that, too. Also, I appreciate your head tap from earlier. The reaction is, if reactant is the output, what's the input called? The reactant is the input, sorry. Reactant, so here, I can show you something. Back on this blank page. We in chemistry have a standard kind of way we show reactions. So let's take, let me think here. Let's say we have, I don't remember the photosynthesis reaction, but this is the reaction for respiration. So you have glucose, which is C6O, C6O5? Oops, I can't erase. C6O5H12. I believe. That might not be exactly correct. And then also you have oxygen. So this side of the reaction is the reactants. And then they turn into H2O plus oxygen in some amount. Let's see, that's... no, not H2O, oxygen, I'm sorry. CO2 and oxygen. You can see there's 6 carbons on this side, so there must be 6 of these CO2s at the end. Like this. Boop. And there we had 12 hydrogens before, and we're making water, which has 2 hydrogens. So we must have 6 of those. And there you go. That's respiration. On this side, we have the reactants. Boop. With this arrow symbolizing, I mean, this is like the process, basically. This is them turning into the products. Does that clear it up at all for you, Arca? I hope it does. So this is the standard way we would write a chemistry equation, pretty much. This is what I did all the way through university. This is just how we do it, pretty much. Standard convention. So, in that case, if we recall from before, the correct statements are 2 and 3, which means the answer should be B. And we can move on to the next question, shall we? Use the following information to answer question 2. The oxidation of ethanol, C2H5OH, this little L means it's a liquid, to ethanol, C2H4OOL, can be represented by the following overall equation. Hey, here you go. Oh, for photosynthesis, shouldn't 1 be false? Yes, for photosynthesis, 1 is false. The reactants are glucose and oxygen. That's incorrect. So it's only 2 and 3 for B. Oh, I think that was a stream delay thing. Okay, so here you go. These are the reactants. Oh, god damn, it's hard to write like this. Reactants. Yeah, good enough. And these are the products. Oop. There you go. Juicy. Yes, it is. This is... I wouldn't drink either of these. I'm pretty sure both... Oh, ethanol. Ethanol would be good. I wouldn't drink ethanol. That would kill you. I'm pretty sure that would kill you immediately. So this is the equations. The enthalpy change for the oxidation of ethanol and the overall equation is... So the enthalpy is... so it's a little complicated. It's got a fancy name because it's slightly more than this, but generally it's considered to just be the amount of heat the reaction produces. So if you imagine turning on, say you have a stove like this, boop, 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 and it's a gas-powered stove, so it's lighting a fire under the water. These fires under the pot are releasing heat as they go. So they have what we call is a negative enthalpy. So enthalpy. I'm not sure that's quite right. I'm not sure if it's a negative or positive enthalpy actually. But basically this is what we're referring to. We're talking about how much heat comes in. Or alternatively, how much heat gets absorbed by the molecules, say if bonds are formed. Like in photosynthesis, where it absorbs that sunlight energy in order to form those bonds and create sugar that it uses to power everything throughout its body. So that's what the enthalpy is pretty much. Given that, you can look at these delta H's. These are the... This is the enthalpy, so this is how much heat it is releasing, basically. So if you look at it like that, we just need to... one moment, please. We just need to see what one molecule of ethanol basically goes through and how much heat basically just that part does. Then we multiply it to see the so that we can get the overall idea of the heat of reaction, basically. So you see, first of all, it goes through this process to get broken down into oxygen, water. Oh, no, sorry. These are comparative, sorry. So if you imagine, just like sugar, this molecule, ethanol here, has some amount of energy trapped in it, just like sugar. And when you digest it, you can break that down into some amount of energy, like a battery, to power your body. That's what you do. Ethanol does the same thing, and you can break it down by burning it, which is basically the same thing as respiration, into these, and produce this much energy from it, basically. You can do the same thing with ethanol, but because it's got slightly less energy in it, it's less effective at storing energy, you get less energy out of it afterwards. So if you wanted to, so if we're talking purely theoretically, if you wanted to turn ethanol into ethanol, you lose this amount of energy stepping down because it's no longer stored in the molecule, basically. You've let it out once you've turned that ethanol into ethanol. Given that, the enthalpy change for the oxidation of ethanol to ethanol this way, you can see it has this difference of 4.8 kilojoules minus 1078.4 kilojoules, which gives us approximately A, I believe, would be the answer. I believe that would be correct. I'm sorry if that explanation wasn't great, but I tried my best. And I hope you're enjoying the examination. I did take this a long time ago. I do not remember all the specifics about this stuff. These little specific details of like this precise numbers of enthalpy come up less and less as you go further on, because you're just kind of like aware of them in the background, you know? So I haven't thought about these numbers directly for a very long time. How's everyone's week going, by the way? I've been trying to sell off a bunch of my stuff in my apartment, and I got 2 offers on the same day. One to take like my little couch set that I have, that I actually got free from my neighbor, by the way. So I made money on it, I guess. And then one for my office chair, and I agreed to both offers. That means I literally do not own any chairs anymore at all. Free money. Yeah, you get it, Gregory. But now I don't own a chair, so I had to borrow one from my neighbor. And let me tell you, it is not very comfortable. I really wish I had my office chair back, but alas, if I had it, I don't know how I would ship it home. Like, I couldn't fit it in like a shipping box to get it home, so... Are you streaming from the floor? That would be funny. I wish I had like what I wish I had one of those like Japanese short tables I could kneel under. That would be very fun. Well, you're a fairy, you could fly. Could be exhausting, I guess. Yeah, can you imagine how tiring it would be to hover in front of a microphone at all times? Also, you would literally hear my wings beating into the microphone all the goddamn time. That would be so annoying. Like, think about how YouTubers have to turn their ACs off while they're streaming sometimes. That, but the fan is pointing directly into the microphone. The ACs, the other big fan, I really am worried about selling. It's a shame I should have sold it in the summer. I didn't even think about it at that time. But it sold way better than it does now. But alas, here we are. Do fairies fly like hummingbirds? What do you mean this is really annoying? Are you calling me annoying, Gregory? Why would you do that? Do fairies fly like hummingbirds? That's how I imagine they fly. I compare fairies like to hummingbirds a lot in my mind. I think they're very similar in nature. Hold on, there you go. Turn myself down a little. I hope that's okay. Yes, the pissing AC. Listen, they don't need to know that. Also, I figured out why anyways, and it's not because there's any issues with it. It's just like condensation. They obviously fly like helicopters. You know what? You're right. Can't you imagine my like 4 wings and my little VTuber avatar being like on a long crank and they just spin around? That's clearly how it works. You could use audio dampeners to block the fan or wing noise. True. I'm not gonna set that up now because I'm gonna move, so I'm not gonna put a whole bunch of stuff on the walls right now. But we'll see. We'll see. Maybe I'll invest in this stream at some point. Who knows? Yeah. Let's move on, shall we? Come on. The student designed a caliometry experiment. So caliometry is basically a way of testing how much energy is in a system. So imagine, say I have like a donut here. Oop. And I want to find out, like, strictly speaking, how much energy is stored in the chemical bonds in this donut. So like when I eat it, that's the energy I get after all. So what we do is we put it in what is basically just like a big insulated block, like a cooler, and you set it on fire, burn it. And that burning process, that oxidation, releases all the energy, which heats up the surrounding insulator, like say water. We measure how hot that water gets, and we know exactly how much energy was contained in the donut. That's what caliometry is. Helicopters are very loud. It all comes together. You know what? You're right. I'm not saying it's true. All I'm saying is I can't prove you're wrong, Gregory. That's all I have to say on the matter. Find the molar enthalpy of combustion of methanol, CH3OHL. The student burned 0.0345 mole of methanol to heat 0.100 kg of water in the caliometer, and assumed that all the energy was transferred to the water. The initial and final thermometer readings in degrees Celsius are shown below. The student's experimental value for the molar enthalpy of combustion of methanol, expressed in scientific notation, is this value. So, scientific notation, as you may have guessed from this kind of format here, is a specific way of writing numbers, which is pretty helpful for large numbers. So let's say I wanted to express that I had $1.7 million. Well, that's basically how I'd write it in scientific notation. I'd say I have 1.7 times, and then you have 10 to the 6, which is a million. 10 times 10 times 10 times 10 times 10 times 10 is 1 million. So this number is definitely 1.7 million. Oop. That's how we write scientific notation. So, in order to find out the molar enthalpy, basically what we have to do is we have to consider how the temperature changed in the system. So if we look at this thermometer, and keep in mind we have to read any liquid measurements like this, you read them from the bottom of the meniscus. You see this little curve shape here? You have to read the bottom of that curve shape. That's just the standard. That's where it's the most accurate. So this is just under 21 degrees Celsius. That would make this 20.9 degrees Celsius. 20.9 degrees Celsius. And then afterwards it is right here, 73.1 degrees Celsius. So the difference between these is 2.2 degrees Celsius? I think that's right. I don't have a calculator on hand. If anyone knows, you can check for me. Okay, so that's what the temperature change was. Then we also know that it was a kilogram of water. More water takes more energy to heat it up, basically. So if you have to consider how much you have, basically. You only had this fraction of a kilogram of water, so we have to scale down our calculations accordingly. In fact, wonder if it's here. There's normally like a little information sheet that has stuff like the specific heat capacity of water. I do not see it. I don't know why it'd be in the middle of the test, I guess. So I don't know why I'm looking so slowly. Those are the answers. Introduction, contents, blah blah blah. Nope. Damn it. Well, if anyone knows it, shout it out. But we'll just call this whatever for now. Nope. Whoop. What am I doing? Don't do that. Give me the pen. Why would you do that? There we go. That's better. A kilogram of a kilogram of feathers. Clearly, the feathers are heavier because you also have to carry around with you the weight of what you did to those poor birds. No, it won't. Look, it won't let me write here now. What'd I do? Oh, I think I finished this drawing. So I have to, shit. Okay, well, it was, 52.2 degrees Celsius. Thank you, I broke everything. I don't know the heat capacity of water. Hold on, we can look it up. Heat capacity of water. I hope nothing weird came up in those search results. I didn't look it up. 4.186 joules per gram Celsius. So we'll just round that to 4, just to make the math a little bit easier, okay? Shit. It wants the exact number. Well, I'm gonna round it anyways. Fuck you. And 50 Celsius, just to make the math easier. So it's 4 joules per gram Kelvin. Per gram Kelvin. Man, my boss is on me about getting this done this week, but I'm so stuck right now. What's the issue right now, Arca? What are you working on? I don't even know. I don't think I have any idea what you even do, to be honest. Alright, I hope you're gonna be okay though. Best of luck. So We can look for how to use this calculation basically just by looking at the units. We can see that if we imagine that we have to end up canceling the units afterwards. So we have like 50C as one of our inputs, or well, let's say 50K is one of our inputs. And we also have 0.100 kilograms of water. That's 100 grams, by the way. A kilogram is 1,000 grams of water. And we have and then we also have our joules, but we want joules per mole of ethanol that we did. So we also have to divide this all by our 0.0345 moles of our substance. So given that equation, that makes us have 50 degrees Kelvin multiplied by the heat capacity, 4 joules per grams Kelvin, and then we have times 100 grams of water, and then that's all divided by 0.0345 moles. I need to tweak some software for a feature, but the software itself is not working right now. SMH everyone and everything. I feel you, Arca, trust me. Didn't know you did stuff with, what, software design? It's interesting. I hope you the best. I can't help you, sadly, but hopefully everything works out for the best, Arca. I'm sure we can do it. We can make it through this. So then this will give us some answer in the form of the Kelvin units cancel out, the gram units cancel out, and we are left with an answer that is in the form of joules per mole. And this wants kilojoules per mole. So in order for it to get kilojoules, kilo means 1,000. We just need to also divide it by 1. We also have to consider, hold on, it will have joules per mole, lay up our answer in joules per mole. And if we want it in kilojoules per mole, as we all know, that in 1 kilojoule, we have 1,000 joules. So, in order to get these units right, we just need to divide by 1,000, basically. And this gives us our answer here. I don't know the exact number. If you really feel like it, you can calculate it on your own. But this is how we get it. We need to pick up the pace a little. I understand teachers now. I understand why teachers never had enough time to go over this stuff. Hopefully you're learning the chat. I would implore you to consider a lot of this stuff, even if it doesn't seem directly helpful. The methods of problem solving are still extremely helpful, and I would recommend keeping them in mind. I think about a lot of stuff in the same vein as I think about chemistry now. It's much influenced my decision making. Speaking of which, I noticed something, which is I saw a thread on like Reddit the other day, which was like, what are some things that your parents didn't teach you, but you know you definitely got it from them? My mom talks to herself all the time, and I do too. I can't do it. I've clearly picked it up from her. We are clearly both delusional yappers. Yeah. There we go. There's a helpful demonstration. There you go. That's me and my mom. We've done it. Mom is an actual voice streamer? Hey, maybe. You never know. It's happened like that before, right? With the Pecco or whatever. I don't know about that one though. I just find that funny. Chad, is this shit real? Tested 2 metal calorimeters of equal mass by transferring the same quantity of energy to each calorimeter. The student made the following data table for the experiment. The calorimeter that would undergo the smaller change in temperature is a calorimeter made of blank, because its specific heat capacity is blank. Okay. So, I'm not positive what the heat capacities of tin and aluminium are. Did it say? anywhere? I feel like if you want me to answer this question, I would have to know that, unless unless I had this memorized. I guess we could look it up. Heat capacity of boop, 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 boop. Aluminium is 0.9, and of tin it is 0.2. So tin has the lower lower specific heat capacity. Now, as discussed before, but to go into more details, the heat capacity is basically how much energy it takes to heat the thing up. So if you imagine you have a cup of water, then a cup of aluminium. I mean, aluminium would be like solid and it would be hard to have like a cup of it, but just imagine you do. And then I put both of them on the stove from earlier. That flame from the stove is going to make the aluminium very hot very quickly because it has a very low heat capacity. It can't store that heat very well. That's why we would call it a conductor of heat, because the heat flows through it extremely quickly, basically. It gets hot very, very, very fast. Water, on the other hand, does not get hot at all. That's why you would use like ice to cool down your drink, or why they use water to power steam turbines. It takes a lot of energy to heat this stuff up, thus it can store a whole lot of it too. With that in mind, if tin has less heat capacity than aluminium, that means it can hold a much less heat, and if given the same amount of energy, will heat up much, much, much more. So that means that the calorie that would undergo the smallest change in temperature would be aluminium, because it has the larger heat capacity. Boom. Simple, right? It's something everyone can understand. If I'm going too fast for you, please make sure to ask any questions. God, I miss my chair. I miss Goopy too. I like this period in my life. My little time I moved out to Sarnia. I had a good time here. I think it was a good time. I had a good time in university too, thinking of tests like that. I really enjoyed my time in university. I like chemistry a lot. There's a reason why I'm doing a test here on stream right now. Fermentation of fruits and grain convert glucose to ethanol and carbon dioxide, as represented by the following equation, like this. You can see in this equation, we've just included the energy as one of the byproducts, basically. This is, again, just like the heat that it releases into the atmosphere. So this is its power to heat stuff up, basically. So the molar enthalpy of the reaction for carbon dioxide in the fermentation reaction is molar enthalpy. So this is the molar enthalpy, basically, is how much energy this thing is holding inside of it, basically. Like, as said before, it's these bonds, like the ones between the carbon, boop, oxygen, and oxygen, boop, 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 boop. These hold energy inside of them. And this is what the molar enthalpy is referring to. So if you were to, if you had carbon and oxygen and you spontaneously wanted to create these bonds, you would have to put in this much energy to cause it to happen. Glucose, the ferment, I don't know. So I think, because this is ethanol right here, you got the heat capacity for it earlier, right? Or not the enthalpy for it earlier. The enthalpy for the oxidation of, yes, so forming, oh, no, that won't help us. That is unrelated at last. I think there was I remember there being a little handout book we got in high school where this is from, which was basically just a little book that had a bunch of chemistry information on it. And I think this is probably something that was in that book. They stressed being able to look up information about the chemicals, basically. The exact molar enthalpy of a lot of common chemicals. It's a good habit, I guess. I understand why it taught us. I mean, today, being able to look up facts about chemistry is incredibly important, but I don't have this information on me right now. So I think we're just going to skip this question. But I hope you understand from this explanation what you would do to solve it, at least. In order to get the molar enthalpy, what you have to figure out is how much energy is contained in these bonds. And you can do that through understanding its formation, basically. Which of the following is the original source of energy stored in glucose? So, on the Earth, barring a few extreme examples, everything ultimately comes from the sunlight of the sun, because the sun blasts the Earth with tons of energy in the form of sunlight, like, and then plants absorb that sunlight. Hey. Yeah. Do you like my little tree? Oh, collab stream when you move back home? No, absolutely. I will not do a collab stream with my mother. How dare you ask me that? I refuse. And then these plants are what go on to feed every single like animal and mushroom and whatever. Let me draw a... There you go. Boop, 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 boop. There you go. It's Keel, the deer tar. And she has a stick. Soaking up the sunlight. Exactly. And then the deer tars eat the trees. And then this is where all energy on the Earth comes from. There's a little bit of like lava in the center of the Earth, but for the most part, that can't power life because it's all the way in the middle of the Earth. Instead, everything comes from the sun. Even oil is trees that died a long time ago and then got compressed into big patches of oil. So even that oil is sunlight powered, basically. Everything is solar powered. So the original source for anything is the sun. Ooh, up next. Hexane, C6H14, undergoes combustion as represented by the following equation. See, here you can see that same kind of reaction. If you break all these bonds in the hexane to create these compounds here, you're releasing this much heat into the world. Standard molar enthalpy of formation of hexane, therefore, is standard. So this is for 2 hexane molecules. So if you wanted to know what it was for just 1 molar, that's what the molar refers to, is how much of this stuff there is. Enthalpy of formation, all you have to do is divide it by 2. So your answer is C, because it involves 2 hexane molecules. Ooh. Ethylene, C2H2, undergoes complete combustion in a calorimeter. So complete combustion means all the energy, basically. And this is represented in the unbalanced equation. Unbalanced meaning basically all the letters on this side don't add up to all the letters on this side. So for example here you have 2 carbons here. On this side you only have 1 carbon. So how could that be physically possible? You can't make or destroy matter. So it had to have come from somewhere, basically. So if you wanted to balance this out, first you would need to figure out the coefficients. So, as said before, there's 2 carbon atoms on this side. That means you must end up with 2 CO2 afterwards in order to balance out that carbon. Then, same thing, you have 2 hydrogens here, 2 hydrogens here, 1 here. And then you have 3 oxygens. 3 over 2 oxygens. Technically, whether you can have like a fractional molecule of oxygen is kind of meh. It's not like it's really half of an oxygen molecule reacting. It's just that, like, if you imagined a bucket with millions and millions and millions of molecules in it, it takes 1.5 times more oxygen to do this reaction than, like, say, water it produces. So given that, we can say the coefficients for the equation above are 1, 3 over 2, 2, and 1. I bet it probably wants me not to have this be a fraction, but I'm going to use it anyways. Oh, you know what? Yeah, and then this is when delta H is negative 2602. So it is literally asking me to double it, actually, to 2, 3, 4, and 2. See, it's all in ratio. I just multiply it by 2, saying two of these reacting instead of 1. And then that cancels out, transfers to all this other stuff. I hope everyone understands. I was thinking also about how, speaking of monster girls, I was talking about deer tar just a second ago. So, long time ago, you may know, humans domesticated dogs, and domestication is, of course, a two-way street. We domesticated dogs, but dogs also domesticated us. I think my theory is that wolfies. Oh, there you go. Yeah, that's my drawing of a wolfie. You got a problem with it? Wolfies also inspired us to go out and greet the dangerous beasts waiting at our doorstep and go try to be their friends. And this is the moment that made monster girls real. This is what this is what drove humans to desire monster girls and deer tars. It's an evolutionary advantage, trust me. You wouldn't understand, Mom. It's beneficial. It makes me more friendly. That's my theory, though. That's my personal theory. Water. Great. God, I love water. How's everyone doing in chat, by the way? I hope you're enjoying yourself so far. I certainly am. This is a fun little thing. Thank you. It is profound. You cooking? I am cooking. I am the chef, if I may. Molar enthalpies of formations of solutions. So aqueous, like before we had liquid compounds. Aqueous means dissolved in water, basically. So, like, if I have salt, up here, salt, table salt right there, if I dissolve it in a cup of water, it becomes NaCl, aqueous. Which of the following potential energies diagrams illustrates the reaction of hydrochloric acid and aqueous sodium hydroxide? Reaction of hydrochloric acid and aqueous sodium hydroxide. So, the potential energy diagram, like say, let's just take this one here. Basically what's showing us is that there's some amount of energy stored in these products here. And then based on how this arrow moves, it can go up or down, whatever, it just matters where the energy is. This is how much energy is like held in the aftermath. So again, like a battery, like photosynthesis. Therefore, if this goes down, energy must be released out into the world as heat. So that would mean that this process releases heat. We would call that an exothermic reaction. Exothermic. Exo meaning out, and thermic meaning heat. So it's releasing energy. The reverse, however, would be endothermic, because it's taking energy in, basically. Oop. So, given that, we can see that if we look at these molar enthalpies, their formation basically, the formation of the solutions, how much energy is stored in it, dissolving pretty much. Oh wait. Yeah. Yes, we can see that. Sorry, 1 second, I just need to think. Nah, ignore this, ignore what I'm saying. But this other stuff is all true. So, if you imagine these entropies, these are their formation entropies, basically. This is how much is locked in their little cores. NaOH aqueous and NaCl aqueous both have a lot of energy trapped in them. So if they form together in order to form HCl, hydrochloric acid, they won't have a lot of energy stored in them, and as such, they will release a lot of energy out into the atmosphere. So that means that if the other way, I'm sorry. The the HCl has a low heat of formation, and NaOH has this high heat of formation. And if they react together, they'll make this kind of middling heat compound of NaCl. And you would think also, if you imagine you have both of these on this side and two of these on this side, then the NaCl is likely to form because the amount of energy stored in it is so much lower than in just the NaOH and HCl. Nature likes being low energy. We're trying to do reactions that give us low energy, basically. So, therefore, the delta H must be less than 0. It's releasing heat, basically. So it can't be C and it can't be D. And as I discussed before, this actually shows that the energy contained in the sample is going down. So that means it's B. I believe that should be correct. Does everyone understand that? If not, feel free to speak up. I only know if I'm being too confusing. If no one stops me. Speaking of which, I was thinking about high school a little, and one thing I think that changed a lot about me, just a lot about my life and how I think about stuff, to be honest, is I had my AP Calculus teacher, Mr. Ranieri. I can't remember what he looks like. He kind of looked like, he had like a square face, and he had like, not that. Oh, I can't erase on this, but ignore these bits. And then he kind of had like this flat top, and then he's a little short little guy. Boop boop. Hey. He told me that I was taking notes on lined paper, but I was thinking about what I was writing on this lined paper far longer than, or it took me a lot longer to write down on this lined paper than I actually thought in my mind. So I would come up with a thought, and I'd hurriedly write it down in this space, basically. But my thought would kind of leave me by the time I finished. So he said to start using blank paper, because in blank paper you aren't confined to the lines at all, and you could write a lot faster, but it's much messier. And I did this, and it worked incredibly. I love taking notes on blank paper, and it's all I ever do from this point on, pretty much. I don't understand, even to this day, I don't understand why people like lined paper. Sucks. During the revolution, just use blank paper. Just go into your local Staples and buy a massive box of printer paper, and boom, problem solved. You never have to worry about it ever again. I love it. Highly recommend. Enthalpy diagram. Oh, just looking at this, by the way, we can see the products have more energy in them than the reaction does. So that means this is an endothermic reaction. Quick statement about this reaction represented by enthalpy diagram is that it is, well, we know it's endothermic. And also, so when you go up in energy like this means that energy has to come from somewhere. It has to come from the environment. So if you imagine there is like a middle product here, you would first have, you would first have an endothermic reaction here, which absorbs energy, and then a little exothermic reaction here that then makes the products. Though if you consider this all being one smooth action, the whole thing is an endothermic, if that makes sense. So, to do this endothermic reaction at the start, you need to put some heat into it, just so it starts going, basically. It would require more than the reaction enthalpy to start it. Because you have this difference here. Yeah. Oop. Oh, wait. Yes. That is correct. This is relaxing music. I linked it at the start of the stream. I would highly recommend checking out the creator. I was gonna put them in a little, I was trying to work with my Keelbot, where the stream started, but I was having a hard time. That's why I had to turn Maple off. I found a There's like a little volume control. Like there's a little like volume bar in Mix It Up that controls like TTS volume. And I tried playing with it, and it just literally didn't do anything. She was just full volume at all time, no matter what I did. I don't know what to tell you. I'm trying my best here, Chad, okay? I'll fix it eventually one day. Did you know I can actually, now that I think about it, where's my mouse? Boop. Did you know I could actually swap to Viviana at any moment? Ooh, I'm a spooky ghost girl. That's, that's the thing I can do. I don't know what to do with that VTuber model. I do like the way it looks a lot. But I just don't really know how to do it. Alas, I am not Viviana in real life, so it is just a costume. I'm sure I can think of something. Imagine the following reaction. A plus B into D plus C plus D. So, look at these little arrows, by the way, here. These little arrows represent an equilibrium. So basically what that means is that while A and B are turning into these products, C and D are also reacting to form A and B. They're both going on at the same time. It's just a matter of which reaction is going faster that determines what the output is. Technically, literally every reaction is in equilibrium, though for lots of reactions it's simply fundamentally impossible for them to go backwards. So the forward reaction requires energy in it to start going, and the reverse action also requires energy in it to start going. For the forward reaction, which of the following rows describes the reaction type and the enthalpy of the reaction for the equation below? So if you imagine the forward reaction takes in 70 kilojoules of energy every time it does it, but the reverse action takes in 80 kilojoules of energy. This means that the reverse action takes in less energy, or the reverse reaction takes in more energy, and since nature likes the low energy pathway, it will favor this top energy reaction. So it is more likely to proceed forwards than backwards. And since you are since basically you are releasing energy as you go forward, that means it's an exothermic reaction. Which means... Oh no, sorry. Your activation energy is still positive then, which means that you have to take in energy. But as a whole, you do get energy out because... Wait. Reaction. Yes, as a whole, you do get energy out because you're undoing this reverse reaction pathway, basically. Every time you do the forward reaction, you're undoing the reverse reaction. Therefore, this is an endothermic reaction that has negative 10 kilojoules of energy, I believe. Truth be told, I'm trying my best with these questions. I don't know how true these are going to be a lot of the time. Ooh boy, how much do we have left? There's still a lot left in there. We might not make it through all this, but I'll do my best. Okay, chat? Well, when we need to stop, we'll stop, but I'll do my best until then. Using the following information, answer numerical response. Question 3. Using the numbers above, match the statements above with the descriptors below. There's more than one correct answer. Okay, let's read the statements. Enzymes speed up digestion without being consumed. A burning match is placed in a pile of wood to start a fire. The catalyst is used in the Haber process to produce ammonia. Electricity from the battery is used to ignite the fuel of a car. Interesting thing about the Haber process, or actually, I learned it is the Haber wash process. This is a reaction that turns nitrogen, like the hydrogen in the air, plus hydrogen gas, 3 of them in fact, into ammonia, 2NH3. Ammonia is super important because this fertilizes plants, like say, corn. Here, let me try to draw corn. Yeah, that's me trying to draw corn. Perfect. So if you want to grow a lot of corn, you need to put a lot of ammonia in it. And if you want to feed a lot of people, then you're going to need a lot of ammonia. This was an extremely difficult process, though. And eventually, Haber and Bosch came together using an iron catalyst to actually make the reaction work. And then the human population on Earth skyrocketed. This is the invention that has most substantially impacted the amount of people on Earth. And this is like the golden chemistry reaction. This is like the chemist's claim to fame. This is the good one. Using the numbers above, match the statements above with the description below. Examples that model activation energy in a chemical reaction are numbered. So, activation energy basically means that you have to put energy into them before they start pushing energy out. So, for example, if you use electricity from a car battery to ignite the fuel in your car, you're putting in that electricity energy to get the fuel from the car back. So, that's 4. That one also fits. And then, a burning match placed in a pile of wood to start a fire. That is also an example of you need to put in that energy of the burning match first in order to get the result. So that's a 2. Then also you have examples of alternate pathways. So an alternate pathway means, imagine you have, do I have a little space under here? I do. So imagine that reaction, A plus B. And just for simplicity, let's say they turn to C. Boop. You can see with this reaction pathway, we have this little bit of activation energy you have to put in. They have to go up a little bit in energy first to form whatever this thing is, this AB compound. But let's say that they don't have to form this way. Instead, I could put in and under different considerations, AB can form with only this much energy. This is an alternate pathway, and this is also a much more energy efficient alternate pathway, which means the reaction will go much faster. That's what an alternate pathway is. So given that, an enzyme would be a good example of this. The enzymes in your stomach help break down food easier, meaning basically they need less energy to start breaking down. It is also true for a catalyst using the Haber-Bosch process. This iron, it helps reduce the energy required to make this reaction go. So that's 1 and 3. I hope that helps. A technician set up an experiment to test the reactivity of some uncommon metals and their ions. The technician recorded the following data. Reactivity of some uncommon metals. So this table shows you whether they did or did not react together, when basically they just push them together. I guess these are aqueous, so I imagine a beaker with this dissolved in it, and then just dipping a rod made of that into it. So, when listed in order from weakest to strongest, the reducing agents above are, so, I always remember the saying, oil, rig, oxidation, I spelled that wrong, I think, whatever, you get it, is loss, okay, hold on, it's loss, there you go, just for just to make clear, loss, fuck me, loss, there you go. And then reduction is gain. So what's it referring to? Being gained or lost? An electron. If you get reduced, you gain an electron, and if you lose an electron, you have been oxidized. The reason why they're called this is because oxygen really likes to steal electrons. It likes it a lot. It's very electronegative. So that's why it's called oxidation. And it's called reduction just to confuse you, I guess. Or when reduction is gaining an electron. But So in that way, a strong reducing agent, so something that can reduce a molecule, is something that can gain a molecule would be something like a reducing agent is something that would give an electron to a molecule so it undergoes reduction, if that makes sense. So which of these compounds are most likely to give up its electrons? Well, electrons are negative charges, so remember that. That means that if it gives up its electrons to become positively charged, it is a good reducing agent. So if it gives up its electrons, it is a reducing agent. You can see here then that since solid zirconium, is that what that is? Zirconium? I think so. Solid zirconium, when reacted with these positively charged molecules, it will give up the electron here. It'll give up the electron here. It will give up the electron here. That means that it's a strong reducing agent. Similarly, we can look at it from the other side. If zirconium is a good reducing agent, then zirconium 4+ must therefore be a bad oxidizing agent, because it doesn't want those electrons back. It readily gives them up, if that makes sense. And as we see here, no reaction, no reaction, no reaction, no reaction, because it's barely capable of oxidizing anything. It's a reducing agent. So it must be B, zirconium solid. Oop. If these metals and their ions were placed in a table of standard electrode potentials, the half reaction with the highest positive electrical potential would contain the strongest blank. When compared to the hydrogen half cell, this half reaction would be located blank. So, electrode potentials. Let me tell you very quickly about how a battery works. Boop, boop, boop. I hope the name of my stream is right. Is the name of my stream right, by the way? I always get that wrong. It's like so many ways to do it, but like I think I always just forget to confirm it. I think that's the big thing I miss. I'm live with just chatting. Hey, fake chemistry school. Perfect. Okay. Never mind. I'm perfect in every single way, and I never do anything wrong. Please remember that, chat. So, a battery works like this, basically. You have you are working off the reaction of two metals. Well, let's just consider two metals. Like, say, I don't, well, I guess we can use these. So let's say, it's hard to work the scroll wheel like this. Zirconium and iridium, sure. Zirconium, let's say zirconium is this solid piece here, this solid rod here, and we'll say that we have iridium, the 3+ in here. So as we can see from the reaction table, this iridium 3+ really wants these electrons, but this zirconium metal is really ready to get rid of them. It's a reducing agent. It's such a powerful force, in fact, that it's able to send electrons down this wire here. Has to load, say, like a light bulb, lighting it up, and then eventually the electrons find their way to the iridium in here, react with it, and form iridium solid. And this is what a battery is. This is how we can get electricity from chemicals. Now, if you imagine the electric potential, this is how good the thing works as a battery, basically. So, as said before, zirconium is a really good reducing agent. That means it works really well at giving up electrons. However, the -2 is very bad at receiving electrons. So zirconium would be really bad to have on this side of the battery. Generally, we talk about hydrogen half cells. That just means that you're imagining the battery on this side is turning H2O into 2H2O, in fact, to 2H2 plus O2 gas. Is that right? No, that's not right. Turns into, yeah, 2H2 plus 2OH minus. Not right. H2O, H2OH minus. We're basically talking about it in reaction to how, if the other half was water, basically. It's just a standardized table. It doesn't matter where the reference is. This is just the one we're using. So something that works is the better battery has a higher positive electrical potential. That's the important part. So therefore, on the compared to the hydrogen half cell half reactor. So basically, we want this side to be a really good reducing agent, which would mean that it would have a higher electrical potential than the other side. It wants to do this reaction, basically. Sorry, I feel like I might have said that a little confusingly. If you need me to rephrase that, please say. See, rephrasing. I went to Subway again recently, and you know they renamed their their sandwich, like their main sandwich I had, the one I always had. It used to be called like a Subway Mill, and now it's called like a Great Canadian. And every time I order it, I feel like I've been pandered to. But at the same time, it's also like the only good sandwich. So I feel like no matter what I do, I have to like support this patriotic option, even though I don't really embrace the ideals of it very much. It's very much a corporate gimmick. But alas, here we are. They also have like, I mean, like most Subway sandwiches suck. Like the bacon and turkey and ham and stuff are good. I don't really know what else people would get. Like if you get like one of the like crispy chicken sandwiches or whatever, don't those taste really bad? Who gets those? Is that like also like the people who go to Arby's? They're among us. They're just like people like you and me, but you'll never know who they are. The only difference is that they're going to hell. You know? You feel me, chat? You feel me? I think you feel me. Certain bacteria remove nitrogen from nitrate iron ions in soil and release nitrogen as a gas, as represented by the incomplete skeletal half diagram below. So it's incomplete skeletal. Basically, this isn't balanced at all. You see, this side requires oxygens in it somewhere. This side has oxygens. This one does not have any oxygens. So it's not complete. It's only part of a reaction. During this reaction, the bacteria cause NO3 to undergo something, and as a result, the oxidation number of nitrogen will do what? So, oxidation number. Let's imagine that. On the periodic table, I don't have it with me, but basically, what's important is the idea of valence electrons. Carbon, in particular, has 4 of them. These valence electrons, you can imagine they're ready to be paired up with something. So with things like, say, an oxygen comes up to it, it can use its ready to bond electron. Come on, there you go, like this, and they can come and form a bond together. In fact, they could even form, if they have 2 available electrons, they can even form a double bond like this. Or more oxygens can come up and do the same thing, creating carbon dioxide, CO2. So, you can see then that the oxygen bonded to the carbon. That's what we call oxidization, because the oxygen is pulling on these electrons really hard. They're really, really, really weighted towards the oxygen side because oxygen wants them so badly. This means that this carbon is actually kind of missing its negatively charged electrons, which means that this ends up being a little positive, and these end up being a little bit negative. Which is important. It actually affects chemistry massively. So when we think about the oxidation number, what we're thinking of is how many electrons have basically been pulled away from this carbon pretty much. not completely, but that the carbon doesn't control very well. You can see there's one electron here, one electron here, one electron here, and one electron here. So the oxidation number is, I'm not sure if it's 2 or if it's 4. It might be per 2 electrons, but we'll just call it we'll just call it 4. I'm pretty sure it's 4. I'm pretty sure it's per electron, but I think the oxidation number is 4. So in that case, you can see that the oxygens from this nitrogen are getting popped off it. If its oxidation is going down, then it must be getting reduced, in which case its oxidation number is going down. In fact, it's going from having 3 oxygens attached to it to going none oxygens attached to it. The oxidation number is going down extremely. It's undergoing a reduction reaction since it's losing those oxygens. Oops, so yes, C is the answer. Which of the following rows identifies the coefficients of NO3, H+, and E- when the nitrogen half reaction equation is balanced in acidic conditions? So, balanced in acidic conditions. Basically, acidic conditions mean we have a lot of H+ just floating around. So we can just throw them into the reaction pretty much. Oop, NO3 minus. And again, acidic, or these are all aqueous compounds, as we've shown with this. These aqueous. So that means that also it's in a vial of water, and we can also just bring in H2Os to the reaction. So if we have NO3 to N2, well, there's 3 oxygens on this side we need to deal with. So that means that we must end up with 3 H2Os on this side, right? And then also on this side, we end up with let me just make this through. We need to end up with 6 hydrogens, so 6H+, like that. So this NO3 combines with 6H+, and how many electrons? Oh, with 4 electrons, because it needs to, basically, if you imagine, these oxygens are pulling on these nitrogen's bonds. Boop, 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 boop. Pulling on these bonds like this. So if you want to release this oxygen and have this one break off on its own, you have to put an electron in it to convince it to break off, because it will not accept having less than these electrons. Therefore, since I'm reducing the oxidation number from 4 to 0, I have to put in 4 electrons somewhere in the NO3 minus. Wait, but I have 6 positive hydrogens coming in. So actually, that's incorrect. I need to balance out these charges. I have 5 electrons coming in. Because that way, these 6 positive hydrogens counteract with the 5 negative electrons and this negative NO3 to give me these neutral conditions at the end. So the answer is A. I hope that made sense. What else have I been up to? Oh, I was, yesterday, I walked to the weed store because I was like, man, I need some weed for these conditions, you know? I can't be expected to do it like this. And, I was still feeling a little unwell, so while I was talking to the weed guy, I threw up mid-conversation. Hilarious, I know. Oh, I felt so embarrassed. I felt so bad for him, but I know he was like, no, don't apologize, it's fine, and everything like that, and everything went smoothly. But god damn, man, that was not very fun. Ugh, I think I know what made my tummy so upset. I think it was a local restaurant. Hopefully it's not this new medication I'm on, because that sure would suck. I'll try my best. I'll try my best, chat. I'll try my best to live. How much longer is this test? There's been a good amount of it, but I don't think we're gonna make it through it, chat. I'll be real with you. But we've made it through what we can, and that's what matters, okay? Here's the following information to answer the following questions. The equation numbered above that would not represent a redox reaction is blank. The equation classified as a disproportionate reaction is disproportionation reaction. Let's start with a redox reaction. A redox, as the name kind of implies, means it involves reduction and oxidation, or rather that an electron is moving from some species, like say a carbon, over to an oxygen. That means that a redox reaction involves, for the most part, let me see. This question is going to take a second. So yes, some electron needs to be moving from one compound to another to make it a redox reaction. And thus, we can look at these and think, okay, so if you think about this potassium metal here, this is reacting with these chlorine gases to form 2 KCl's. But if you imagine the I'm actually not sure on this one. What do you think about this one? Why'd they look at this? Look at how they wrote water at this second question. Who would write it like this? H-O-H? I would normally write it H2O, but you do you, I guess, test makers. So you can imagine this one is this potassium metal dissolving in reaction with the water to form KOH in aqueous solutions. That means it's nice and dissolved up, and also hydrogen gas. However, before this compound was KOH and H2O, the oxygens were stealing the electrons from these hydrogens, basically. But now, instead of stealing the electrons from these hydrogens, they're stealing them from this potassium, which means, in effect, potassium has given electrons to this hydrogen, making it a redox reaction. Then 3 is the reverse reaction. And as we've talked about before, reduction is the opposite of oxidation. So if one's a redox reaction, they both are. These 2 other reactions, though, represent chlorine grabbing onto the potassium. But before, the chlorines were kind of already grabbing onto themselves. Like, these electrons have not changed hands, basically. These potassiums... No, I don't know. No, this is right. I'm not totally sure on the explanation why this isn't a redox reaction. This is one of those things, technically everything in chemistry is a redox reaction, and this is an oversimplification. In reality, everything can be thought of as a redox reaction. It's just about how much like one it is. And if one involves oxygen specifically, it's a lot like one. So either reaction, so it can't be only reaction 3. And then a disproportionation reaction. Disproportionation means basically it's dissolving into the water. So if you imagine you had salt, like boop, boop, and these have a bond, disproportionation would be this bond just going apart. We don't need each other. We'll just dissolve into the water. Thank you very much. And in that case, only for, disproportionation reaction. Yes, only reaction 4 is that, because it's KOH dissolving into, yes, it's dissolving into, no. Well, I'm pretty sure it's B, but I will admit, I'm not 100% confident on this one. I'll be real with you. I'm not perfect. I'm not perfect in any way, and that was a little bit of a guess, I think. I know, right? Sue me. I'm not the best tutor in the world. A 10 milliliter sample of acidified sodium oxalate is titrated with 0.002 molar solution of potassium permanganate, as represented by the following equation. Like this, the initial and final burette readings are shown below. Boop. In the titration experiment, the burette is filled with blank, and the endpoint is reached when a single drop changes the color of the sample to blank. So, burette is filled with 10 milliliter sample of acidified sodium oxalate is titrated with the solution. The titrated, fancy word for added to. It's just a specific way of adding something to a reaction. So the thing added is the potassium permanganate, which means the burette is filled with potassium permanganate. Boop. So it can't be A or B. The endpoint is reached when a single drop changes the color of the sample from, let's see, what do we have? We have, potassium permanganate. Potassium permanganate is actually a bright purple compound, isn't it? I don't know why it'd be pink then. But, let's see. Solution entering the initial and final. I'm not actually sure what the color would be. I think that would be another thing inside the information booklet. But basically, when they're talking about the endpoint, they're talking about, if you imagine, boop, 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 I add in like a drop of chemical, and then when it's added, it immediately reacts with whatever is in here and consumes it. Then, as I keep slowly adding this chemical, eventually this beaker will be completely empty, and all this stuff in it will have been used up. And instead, what I put in will just go straight into the beaker and just sit there instead. This is what the endpoint is referring to. It's basically a measurement of exactly how much stuff there was in there before the beaker. That's the important part of the question. I don't know the exact color change it would be though. We've done a question like this before with the caliometry one. This would be a large one, but I do wish to remind everyone, when you're taking measurements of a liquid device, pay attention to the meniscus. It has to be at the bottom of the meniscus here. This is the reading. This is the reading. Very important. Very important for all of chemistry. Peroxyl indicator can be used to test for corrosion on iron surfaces. Peroxyl indicator contains potassium ferricide, which turns blue to indicate the presence of aqueous iron, and phenolphthalein, which turns pink in the presence of OH-, aqueous. Students set up an experiment in which iron nails were placed in petri dish with a water-based gel and allowed to sit overnight. Peroxyl indicator was added to each petri dish, and the following table is compiled. This shows contents and the color after the formation. Each of the following equation represents the reduction half of equation that occurs in petri dish number 4. Well, in petri dish number 4, an iron nail wrapped with chromium wire, H2O, and O2. So that would mean that if I have, let me think for a second here. So if I have an iron nail in a solution of water, boop, 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 and I think about it turning into rust, which is iron oxide, or basically Fe2+. This is your rust, basically. And then that rust, then that rust wants to react with the, this is another one I need that book to find out for. Because, so if you imagine, like we've discussed before, iron and chromium or copper or zinc or whatever all have some proclivity to give up their electrons. They all have that electrode potential we mentioned before. So the one most willing to give up their electrons in this example, say an iron nail wrapped with chromium wire, is the one that works best in the battery, has the best electrical potential. Therefore, when you imagine that when rusting away in the water, like say iron, it's forming this Fe2 plus, and if that Fe2 plus is really good at taking in those electrons, the chromium will flow away instead, react with that iron, and reform solid iron nail. Basically, they'll protect the iron almost. So chromium, as the name might suggest, does not tarnish very easily. So I imagine if you add chromium wire to this iron nail, it won't change anything. The nail will still rust, as you would expect. Need some more water. I've been meaning to go over to Blue Sky recently, but honestly, I've just been too lazy. I've been toasting on Twitter, and oh my god, why do I have so many bot accounts following me? Is there a reason for it? Why do they do it? I don't really understand what the bot accounts have to gain by following me on Twitter. Am I the only one? Like, I truly don't understand what the benefit is it for them. Why do they do it? Like, it's a scam? What's the scam in following me? I don't lose anything when that happens. Well, what's the deal? Iron and bicycle parts come in a variety of colors. The color comes from dye added to the electrolyte during electrolysis. A layer of colored aluminium oxide is deposited to protect the metal from corrosion, as represented by the following half reactions. When the half reactions shown above are used to produce an overall net reaction, the lowest whole number coefficient, V. So, this is an overall net reaction. Ask the why net, either follow for follow or get you to buy commissioned art/music. Yeah, okay. So if it's follow for follow on a bot, what does the bot get out of it? Like, what does the bot gain when I follow it? I understand for those GFX scans, I get a lot of those, trust me. But like, if I just follow a bot that never sends any messages, what happens? I don't know. Also, it's starting to get annoying. Getting all the followers on Twitter, to be honest, all the time, it's starting to get really annoying. That's another reason I want to move to Blue Sky. Hopefully it's not as bad over there. Among many, many other reasons. So, it wants an overall net reaction, basically. So this means that the reaction has to be balanced. Now, electrons are finicky. You can't just shoot electrons out into a beaker of water. They really, really, really need to match up with something. So you cannot just have electrons coming out in your product. So if you imagine that, we have these 2 electrons going into reaction, but 6 coming out. Can't do that. It needs to be balanced with 3 on each side. So that means that since this one has 3 times as many electrons as this one, we just need to multiply everything here by 3 for this reaction to work. So if you can imagine, 6H plus 6E minus plus 2Al solid plus 3H2O turns into H2 gas, or 3H2 gas, plus Al2O3. Some F for F is just amplifying the account metrics. Some are real users who are just seeing it as a growth strategy. Maybe. I don't know. I truly have no idea. Plus 6H plus. Also, of course, the electrons too. Let me just write these in here just for the sake of this. Plus 6E minus plus 6E minus. So, if you look up here though, like say a mathematical reaction, we have the same thing on both sides. Like these electrons, 6 electrons and 6 electrons. Of course 6 electrons become 6 electrons. That's obvious. So we can just cross this out. This isn't part of the reaction, basically. In this case, these are called spectators. Basically, these things themselves are not reacting. We also have the H+, which, again, is canceled out on both sides, so we don't need it. So, in other words, this is our full reaction here. Oh, I did write the electrons. The aluminum with water forms hydrogen gas and the aluminium oxide. Pretty simple, right? So the coefficient for the aluminium oxide is... wait, this isn't a balanced reaction. Look at this. You fuckers tricked me. You have 2 aluminiums on this side, but only 1 on this side. This side should be doubled. Damn it. So that means my math is all wrong. I should have 2 of these coming out at the end. Then also that means this needs to be times by 2. Again, 2. So we have 6 H2 coming out. And 6 H2O. That should be balanced. Because we have 6 oxygens here and we have 6 oxygens coming from the water. Yes, that is balanced. I apologize for that. So that means the coefficient of H2O is 6. Coefficient of H2 is 6. And the amount of electrons transferred. As we were saying here, we have to account for these electrons here. So for every mole of the reaction here, we have 12 electrons reacting. That's the 12 going from one to the other. So the total moles of electrons transferred is 12. And that's your answer, I hope. Standard cell potential for the cell listed above is, this is another one you would need a guide for, but basically you can imagine the aluminium has a cell potential. It can work to give electrons away to the SN2+, or the other way around. I'm not sure which one is the better reducing agent. How much of it gives out is how much this kind of electron releasing an electron reaction gives out, and how much this pin receiving an electron gives out. So if you wanted to calculate the potential of a battery based on this, the voltage output basically, you would just need to consider how much voltage is created by both of these actions, which I don't have for you right now, sadly, but I hope that does help you answer the question. Electrochemical cell, drawn here. Whee! Oh, they drew a way better battery. This is a way better looking battery than the one I drew. I should have just taken you here. What else did what else have I been up to this week? Oh yeah. So I haven't taken, nah, I don't want to talk about that quite yet. Where's my mouse? Oh, yeah. Oh, yeah. This week I actually stole a toy from my kid. I think I told Tia this story. Might even talked about it in the Discord, but I ordered McDonald's one of these days, and when I got it, I got the wrong order. So I had to eat whatever but the other family ordered, and I guess that family had a kid, and they ordered a Happy Meal, and it had a little Bowser toy, like a little Bowser Mario Kart toy. Yep, that's how I drew a car. Deal with it. This is what cars look like now in Bloomverse. So I got a free toy. I already broke it, actually. I blame the fact that it's fragile garbage, but the little guy, like this part of the car, broke off from the bottom part. So I destroyed a kid's toy already. I truly am an apex predator. Ooh, I need water. I might run sore from all the carrying stuff around I've been doing. The cell above, the reducing agent, bleh, electrons, and the oxidation number of the oxidating agent is bleh. So the reducing agent, remember, reduction is loss. Oxidation is lost. Reduction is gain. The reducing agent is able to give up electrons. So what's the thing giving up electrons here? This would be another thing in the book, I think. Hold on. Yeah. Because if you imagine, in that book, it would tell me which of these is the better reactant. But the reduction agent loses electrons, so it's not A or B. and the oxidation number of the oxidizing agent. So it's capable of making something oxidize. So it's capable of taking electrons, meaning the oxidation number goes down. Yeah. So it's C. Anyways, though. Cool. In the operation of the cell, the nickel electrode acts as the blank, and the color of the electrode 2 electrode solution becomes. This would be in the information book. I'll just so the answer to one here, whether it's the anode or electrode or cathode, it depends on which one is better at losing or gaining electrons, basically. And the cathode is the one that gives up electrons because it becomes positive. That's how I remembered it. But the anode is negative. Because, I don't know, Anne is bad. What do you want from me? Fuck you, Anne. And if you imagine the color of the solution, basically, if you imagine that more nickel 2 is getting added to the reaction, if you imagine it's giving up its electrons to become nickel 2, the solution will become darker because there's more nickel 2 in the water. Meanwhile, the inverse, if it's taking in the electrons, the nickel will become the solid and the color will get lighter as more of it is removed from solution. During the operation of this cell, the species being reduced is 1, and the mass of the copper electrode is 2. Statement above is complete by the following information. Again, this would be saying in your book which one specifically is being reduced. However, again, it's the one that's best able to take in these E- charges. And whichever one that is, the species being reduced, so the thing that's taking in the electrons is going down, and the mass of the copper, if the copper is giving up the electrons, that copper solid is turning into Cu2+. So if you imagine it's giving up the electrons, the mass of the solid copper electrode would be going down. Hay and pennies were originally 95.5% copper, but later became only 4.5 copper in the form of copper plating on steel. The time in seconds required to plate 0.106 grams of copper on steel using a current of 15 amps is... Okay. Another thing that would be in the book, basically, if you imagine, this amperage is an amp is an amount of electrons per time, basically. Electrons per... It's moles of electron per second, I think, is what an amp is. So, if you imagine 15 amps is how many electrons it's able to hand off to the Cu2+ in order to turn it into the solid copper plating. So every time it does this, it needs 2 electrons. So if we're only getting in this many electrons at any given time, we can use that to calculate how many there would be mass here. Oh, yeah, I need to know the density of copper for this. So I couldn't do this calculation without the reference book. But this is how you would do it. You would basically find out how many electrons this mass of copper needs to do this reaction, and then consider how long it would take for this amperage to supply that many electrons. Hopefully that's understood. Bake for head pats more is is one of my notes. That's a good note. I'll keep that down. Yes. Please. Head pat. Then I'll go this thing. Please head pat this thing. Perfect. That's crucially important. Oh wait, exclamation mark. Blue hats. That's what we want. The citric acid cycle produces energy for living cells. Succinic acid, C4H6O4, and coenzyme Q10, CoQ10, are important compounds of the citric acid cycle. Two half reactions involved in the energy production are represented in the following equations. So, if you imagine, the oxidizing agent in the overall reaction is so the oxidizing thing is a thing giving up electrons. So basically they have these potentials each. I don't remember. I think the anode is the one that goes negative pretty much. So if you imagine this has like plus voltage. That means that if I wanted this reaction to go, oh, good Pat, something I actually understand. Tia, if you need help, feel free to ask questions. I wanna make this experience as good as possible for you. I will go back to the basics as much as possible. Also, thank you for the blue pats. As I was saying, so this is how much voltage it would take in to no. This is, I think, how much voltage it would put out. I'm not positive, but I'm pretty sure that this would make a battery that would work spontaneously, because it's putting energy out into the world. Energy out is a good thing, because that means that at the end you end up with something that's low energy. This one, though, is less effective at that. So basically, we're going to have the opposite reaction happening. And although it's going this way in the writing, if we use it as a battery, this would work in reverse, giving where succinic acid gives up electrons instead. And yes, this thing does gain them. Given that in mind, the thing that is, as I just said, giving up electrons in this example is the succinic acid, which is C4H6O4. Yes, this one. And then the voltage generated across the reaction would be 0.091 volts, because that's based on our calculations, based on these, how much voltage is putting out into the world, how much energy it's giving out. Each of the following species could reduce CoQ and CoQ2 aqueous. This is not a question. You want something that's really good, a strong reducing agent, so that it is able to give electrons to these compounds. Therefore, iron 2 definitely wouldn't work, because it is not a reducing agent at all. It would take in electrons instead. It would be one of these guys. I'm not sure which. If I had to guess, it was probably copper. Copper is pretty good at becoming Cu2 plus and giving off those electrons. But I'm not sure. That's just my guess. Aqueous bromine was added in the absence of light to a sample of succinic acid and to a sample of formic acid. The line diagram of formic and succinic acid are represented. The acid that would cause the bromine solution rapidly become colorless is blank, and this acid is classified as blank. Okay, so bromine. Bromine is a halogen, which means that it is extremely electronegative. It wants to steal electrons very, 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 very badly. And it is important to note, these two compounds here, these two carbons, which are represented in this line diagram, basically any point in this line diagram is a atom. These two are sharing this bond across this double bond. This is not very stable. So when bromine comes in, it really, really wants to attack this bond and join into the molecule, brominating it, as we would say. Boop, boop, there you go. However, on this one, you see there's no double bond here. That means there's nowhere for this bromine to attack, and it can't do anything. It won't go. So this is referred to as being saturated. It's saturated basically because if you imagine, there's just no slots for anything to fit on here basically. If there was a double bond, something could attack it like this, but there isn't, so it can't. Generally. So that means succinic acid. This would mean that the fermanic acid would become colorless as the bromine disappeared because it's going on the molecule. And that is because it is unsaturated. It has little slots in it for the bromine to fit in, basically. Which of the following groups of compounds contains only organic compounds? An organic compound, basically what this means is it's a carbon compound. Organic means carbon. So there's, in however many elements you want on the periodic table, what, it's 118, I think? If it's organic, it contains carbon. That's what that means. With a few notable exceptions, though, which is if it doesn't have any of these carbon-carbon bonds, it is also inorganic. And also kind of what we more broadly mean is if we talked about covalent and ionic bonds before. If a molecule shares these bonds covalently, that's more so what makes it organic generally. But it's one that doesn't share at all if you imagine two oxygens that are both very greedy and like their electrons very much and won't share. These are kind of inorganic, or let's say these are OH minus. These won't share, and then, let's say Na plus. These won't share their electrons, and so they're inorganic. That's generally what the kind of vibe difference is. So to that extent, some contains only carbon compounds. So with that assumption, some of these things stick out. This here, this ethylene gas, C2, C6. So, okay, let me see. This one here, this calcium carbide, you can see this metal is very greedy, or like, this won't share its electrons equally because it's a metal. It forms an ionic bond. Ionic bonds are not organic compounds, so it's not B. Same thing can be said with this cyanide group here. No carbon-carbon bonds, nope, bad. Same with this carbon monoxide, no carbon-carbon bonds, bad. With this ethylene bond though, we do consider this because it does have these hydrogen bonds, which I guess also count. Oh, but then why does this count? I'm not sure. Because I'm not positive, to be completely honest with you. But I don't know everything. Generally though, carbon to carbon bonds are what defines something as organic. That is what makes it organic. Yeah. I don't know. I'm sorry. I don't know what to tell you, chat. Oh, come on. We still got a lot left, don't we? Yeah. Well, I think we're coming to a close here on the stream, though. So I might just take a quick look over this and see if there's anything else in particular I'd like to talk about. I think... Oh, this is organic chemistry stuff we're getting into here. Ooh. So, okay, let's touch on this briefly then. So let's take, imagine a long organic compound. Let's start this the other way. Let's imagine water. So, as I discussed earlier, this oxygen is very electronegative, which means that it pulls heavily on the electrons on these bonds, making this more negatively charged and this more positively charged. This actually affects how water joins together in solution. So if you imagine, say, if you had a block of ice, the oxygens from water molecules will actually line up with the hydrogens of other ones to form a lattice structure. Boop, boop, boop. And you can say, like, have another oxygen here, and boop, boop, boop. And then this one has hydrogens, and this one has hydrogen coming off it. And this one can connect to another oxygen. They all kind of link up like this. And because they have this little charge effect to them, they make really strong bonds. That's why electron or water is so good at dissolving stuff, because these polar bonds can rip apart chemicals very well. If you imagine a long organic chemical, still like a long string of carbons like this, remember all these points are carbons, carbon, 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 and they have hydrogen coming off them. Neither of these want electrons that badly. They don't care too much, so they don't really charge each other, cause much charge at all. So if you imagine like a beaker full of these two compounds, they aren't attracted to each other very well at all, and they'll spread out. In fact, they'll spread out so much they basically start evaporating off, especially if you have very small ones, like say methane here. This will evaporate basically immediately. However, there is a very small effect holding these together. It has to do a lot with, like, if you imagine there's electrons orbiting around this carbon, and there's this positive carbon molecule here. These will still attract each other a little bit, even if not very much. So, to that end, longer, very, very, very long organic molecules like this boil and melt at higher temperatures. That's why I say you put octane, which is 8 carbons in a row, in your car as a liquid. That's gasoline. But methane gas, which might come through a pipe in your house, is a gas. That's the general part of this. That's important for this. Anything else in here? Plug-in points, that's more of that stuff. This is functional groups. That's a little bit dry. Reactions, esters and stuff. Ranges of... Okay. Yeah, we can talk briefly about equilibrium too. So, we talked about equilibrium before. In a reaction like this. This arrow means that the reaction goes forward and backwards at the same time. So if I have a cup with or if I have a little container with nitrogen, whatever, this compound in it, it will spontaneously be creating this gas, and then this gas will go back to form this stuff. And we're just going in a loop. It just keeps going on doing that forever. So if you imagine that in the top, so if you imagine these two reactions takes some time to happen. So say N2O4 turning into NO2 takes, I don't know, let's say 10 seconds for that reaction to happen. But the reverse reaction, N2 turning into N2O4, takes just 1 second to happen. And imagine that this means the NO2 will start reacting way faster to form N2O4, then it can break back down. And in this case, that means you will start piling up massive and massive amounts of N2O4. In fact, you will get specifically 10 times more NO2. Why exactly 10 times more? Well, if you imagine at the point where you have 10 times as much N2O4 as you do NO2, that 10 times amount of N2O4 will, every 10 seconds, break down. But the 1/10 as much NO2 will do that 10 times in the amount of time it takes this to do once. So this is how much you need to keep the reaction balanced. And thus, if you have like a container of gas of these things, you would expect there to be way more NO2s than there would be N2O4. I hope that makes sense. That's the principles of equilibrium. That is, of course, very important chemistry because technically every reaction is in equilibrium. So it's, not always really true. I always like to think of chemistry as being statistics with a really large population size, basically. What each individual atom might do in a reaction is completely random. But in just like a cup of water, you have so many molecules rolling that dice every second that eventually that we can say the average just comes out of it again. You have an unbelievable sample size, so the statistical average always happens. That's how I like to think about chemistry. Catalysts. We talked about catalysts. Bronsted-Lowry base pairs. This is important. So, what we consider to be an acid in chemistry. I'm sure you've heard the terms acid and bases before. An acid is something that is able to give up hydrogen ions, and a base is something that is able to give up OH minus. This is a simplified definition. You can kind of expand acid-base reactions to being like every single reaction ever, because, but it's not. We'll just stick in this scope right now. Why are these so important? Because these can be made spontaneously with water. So if you imagine H2O can turn into one H plus and one OH minus. Just like everything else, this reaction is in equilibrium. So in a cup of water, you'll have some amount of H plus and some amount of OH minus. Then if I add in a base, like say NaOH minus, I'm adding more of this OH minus, this base, to the water. So I'm going to increase the amount of this stuff substantially. That is what bases are, Bronsted-Lowry bases. And you can do the same thing for the hydrogen half. So if I add HCl to a solution, that'll break down into H plus and Cl minus and make the solution way more acidic. And then, anything else that looks really cool? And then we talked about titrations earlier. This is a titration curve. This is very important. So if you imagine, so if you look at this line, you see it follows, like it goes up and then it evens out. It goes up and then it's even out. It goes up and then it evens out. So if you imagine in these zones here, where the pH is increasing, it's becoming more acidic. That's what a higher pH means. Very, very, very suddenly. This is because you can imagine that there was previously a lot of hydroxide in the water, this base compound basically, which was keeping the pH. Oh, this is backward. There was a lot of H plus in the water at this point, which was making the water very, very acidic. But then I started adding OH minus to it. And at first, the OH minus reacted with the, whatever excess H plus ions were there until, this is a little more complicated. In the water, there's also a solution of, let's say it's ethanol. So that's C2OH4, 5, 6. C2, 1, 2, 3, 1, 2, 3. Yes. No. 8. 8? No, that's 3. I'm sorry. 6. C2OH6. I got this, don't worry. So this has this alcohol group right here. This oxygen, again, really, really, really wants electrons. It wants it so much, it wouldn't be so upset if one of these hydrogens left it, turning into C2O minus H5. So this oxygen is holding on to the electron all by itself. it can do that. It's not too much. Then, of course, balancing the reaction, we get this acid out of it afterwards. In this example, this acid is what's keeping the pH low. So as I add in more oxygen, it's taking out more and more of this ethanol from the system. And that means the amount of H plus in the system is getting lower and lower and lower still. Till eventually there's no more ethanol in the system, and I suddenly start adding hydroxide, a base, and it affects the pH massively because nothing is preventing that hydroxide from just being added to the solution anymore. This is what gives the very distinct look of titration curves. And if you imagine, the same thing is just happening here pretty much. Just another buffer chemical like ethanol is doing it here. I don't know if ethanol it's KOH in fact, which we're working with here. But this is generally, this is like what a lot of chemistry is. You want to know exactly how much of, say, something is in a beaker of water, like say my job, which was say, how much Pb2 plus is in this water? Well, we can just add drop by drop something that reacts with Pb2 plus, maybe something that'll give it electrons, and see what happens. And then eventually all the Pb2 plus is added, these electrons aren't being chewed up by it anymore, and we see this huge peak in concentration for the added electrons. This is titration. This tells you extremely accurately how much of your, say, Pb2 plus is in the water. So this is what keeps you safe. This is like the thing most chemists do. Just so you know. And that's about it. I think that's all I wanted to cover. That wasn't all perfect. I know some of my conclusions were probably a bit confusing. But hopefully you had a good time. I enjoyed doing that stream. That was pretty fun. Next week, November 14th, is going to be the ultimate stream before I move. So after that, there will be a hiatus. November 14th will be the last stream for a while. So I hope you're prepared for it. Also, hope you all had a good day. I think I'm going to try to raid Anise Eidolon if I had to guess. I think she's still streaming. Either way, I'll send you over there. Yeah, thank you so much for everyone who came out. I hope you all had a good day. I'm moving my drawing tab. That's up the stream all right now. Whoop, perfect. And grab my mouse. Make sure mark raid. Anise Eidolon. Did I do this right? No. This is what most chemists do. Okay, so as long as I can hit it with a hammer hard enough to make the electrons run around, I can get a job as a chemist? Yeah! That's all you have to do. Electrons, as I said earlier, like you don't just have electrons floating around in beakers of water. That would be way too unstable. But you actually can do stuff to make the electrons actually pop off like that. And I've seen them, and just electrons are bright blue in solution, which is interesting. Not very useful, but it's neat.